we can start with assignment number 3, the second half of it, and talk about those. That would be one way. And then we could go back to the beginning and kind of march through. But I'm open to other ideas. Okay, so why don't we start with these questions on Chapter 5, and we'll do Chapter 5, and then we can go back. I'll use this, I guess. For this question, I'm going to use this. Now here, we have the example of an energy diagram. So for atoms, like hydrogen, the electron, and sometimes it's represented by saying, well, here's the nucleus, way out of scale. Here's the average radius for the first orbit, and the second orbit, and the third orbit, and the fourth orbit, and so forth. And the electron is normally in the lowest energy, which is the smallest orbit. It can jump to a higher energy instantaneously if it can absorb a photon of the right wavelength. And by the right wavelength, it needs to get an increase of energy equal to what? I mean, maybe you can't read my mind, but E4 minus E1. It has to get the extra energy from E1 to get up to E4. That's what it needs to gain. You see that? Because right now it's at E1, has that much. So it's E4 minus E1. That's how much energy if it were to jump to the fourth. But energy is related to frequency, isn't it? What's the relationship? Do you remember? I'll have these equations on the front sheet, but do you remember what it is? Yes.
Higher the frequency, the higher the energy.
Okay, so it's proportional to frequency, and there's some constant, the value you don't need to know. But frequency is related to wavelength, h, speed of light over wavelength. So to jump from the first to the fourth, it has to have a wavelength equal, that makes this equal. So the wavelength would be equal to hc divided by the change in energy it needs to jump up. Questions about that? Yes?
Can you repeat that last section?
Yeah. I wanted to show how the wavelength of the photon that it has to absorb relates to the energy it needs. So it needs this energy to jump up. It's already here, but it needs to gain enough to go there. So it has to gain how much more E4 is over E1. But energy for photons is equal to h times the frequency. Frequency is speed of light over wavelength. So I substitute, and then I said, this is equal to delta E. So I can solve for wavelength by just manipulating the equation. So I could multiply both sides by lambda and divide both sides by delta E. Thank you. Okay, here's some popcorn to give us a little bit of energy here. I actually have some cups if you want to be more formal and put it in a cup. Okay, and I'll pass this one over this way to help yourself. There are some cups, so you can borrow some from her. Sorry about that, Beth. Okay, so it has to absorb a wavelength of the right energy. If you want to jump to a higher one, you need more energy, so that's a smaller wavelength, because energy's in the denominator.
So if it was like 6 orbits, then it would be E, so 6 minus E?
Yes,
Okay.
yes. Mathematically, that's what it would be. Now, here they're showing us that the more correct way is, instead of orbit, is to talk about energy levels. 1, 2, 3, 4. And as you go up, they get closer together, 5, and so forth. So, this is the way we tend to talk about it. But the same thing, has to gain the right amount of energy to go up. So on here, this one is absorption, because it has to gain energy to go up, so it has to absorb. This one is absorption. This is emission, because it drops down, it has to give off a photon of just the right wavelength, just the right energy corresponding wavelength. In this case, it's dropping down. It's E2 minus E1 is equal to the wavelength of what's emitted. So up, it has to absorb to go up. When it drops down, it has to get rid of that extra energy, and it emits. Is that clear? So this problem, let's see, which B gains energy. I don't have the exact question in front of me. C loses it. E is ionized because it jumps out of the atom. D is not permitted. You have to go up a full level. And by the way, when it comes down, it can come down in small steps or big steps, all the way down. And in more technical physics, there's certain probabilities of what it will do. Okay, just going on to Doppler. We went over Doppler. We didn't spend a lot of time on it, but you had it in reading and in an assignment. And you're given that this is the so-called rest wavelength of some light. That's what it would be. You know, remember how I brought those emission tubes and we looked and saw the wavelengths? If we were in front of the lab and I set that up and you measured, you would measure that wavelength. But if it's moving toward you, you'd measure a little bit shorter. If it's moving away, a little longer. So the ones that are moving toward you have slightly shorter wavelengths. All the lines in the spectrum, so a spectrum of the star typically looks like continuous with some dark lines in it. So if this is it at rest, if it's moving, and this is increasing wavelength to the right, if it's moving so that the lines look like this, which way is it moving?
Right.
Okay, so it's moving
Away.
away because it's shifted to longer. See, all of the lines are a little bit longer than they were. So you had questions that said, which are the ones moving away? Those would be longer wavelengths. Which are the ones moving toward? Those would be shorter than the rest wavelength. Which one is moving the fastest? That's the one that's either moving toward or away by the largest amount. And that would be noted by which one has the wavelength that you observe it minus the wavelength at rest. Which one has the largest value for that? And in math, we sometimes we put something in front that says it's the absolute value. Plus or minus doesn't matter. Whichever has the bigger number is the one that's moving the fastest. So those dealt with spectrum. In this case, and from this, you could answer the question, how is an emission line spectrum formed? And that's when atoms that have their electrons excited drop down, and they give off certain wavelengths which relate to the changes in energy. See what I'm saying there? To produce an emission spectrum, you have to have excited electrons dropping down, and they give off wavelengths, and only the right wavelengths that correspond to the differences in energy between the levels. Absorption, you start with the electrons in low orbits, and they gain just enough energy to jump up to one of the higher orbits or energy levels. But they only absorb the ones of exactly the right energy to jump up. All the rest pass through. So when you look at the spectrum of any one element, it's mostly continuous, and there are some dark lines. But most of it is continuous. It's only certain ones that are absorbed. And then if you mix the gases together, you have a mixture of all the absorption lines. So you have lots of absorption lines then. So if you have a star, or in the case we were doing, if you had a light bulb and a cool gas cloud in front, the gas cloud was hydrogen. On the way to you, it would absorb the lines due to hydrogen. If the cloud was oxygen, with ones due to oxygen, if it's hydrogen and oxygen, then it would absorb the wavelengths of each of those. But we could tell them apart because we could match patterns. We also then went on, so what do we learn from the spectrum? Let's answer that. What do we learn from the spectrum of stars?
Composition and temperature.
Okay, we know what it's made of. We can see what elements are there. Now, as I indicated, when we get to stars, it is a bit more complicated. But if we're clever, we can even find out how much of each element is there. So we can learn the composition, the abundances. We'll see when we get to stars how we can learn the temperature from the absorption lines. But the other way, so the other thing from the spectrum is the motions, right? Motion toward or away from you. If we look at the continuous spectrum, we can talk about what are called thermal radiators. Objects like a light bulb that you heat them up and they glow. And if we had, okay, so I'm a light bulb, there's a filament in it, pretty bad looking light bulb. Okay, and there's light coming out from it. And some of it comes our way, and then we have a prism. And so the light then is spread out into the different colors, okay? From red to blue. So we would get, this spectrum of all the colors. Or, and this is increasing wavelengths, and if we plotted it in intensity, it would look like this. This is wavelength. This is intensity. Now, if I can turn the bulb to higher temperature, what will change about this spectrum, this thermal spectrum?
Shifts left. That peak.
Okay, so the peak shifts to the left, and someone else. One other thing. You get some of this. Pardon? Right. So it not only rises up, but it shifts to the left. And so it would look something like that. If it's the same object, it will be higher at every energy, and the peak will be at shorter wavelengths. Any questions about that? From those two observations, it's higher or more intense, and it shifts, we come up with two relationships, two laws of thermal radiators. One is that says, and I'm kind of careless whether I'm saying intensity or energy. In this case, it doesn't matter. But it's really energy per second, or the power, is equal to sigma times the temperature to the fourth. And we've gone through examples, right? If you have twice the temperature, imagine you have something that's glowing like a star, and you change the temperature, which you really can't do, to twice as high, then it would be 2 times 2 times 2 times 2, or 16 times as bright. 3 times as high, 3 times 3 times 3 times 3 is 81. Yes?
So you use this equation in order to figure out the graph.
Well, from the graph, this tells me how much energy it gives off. But I'm not going to ask you to plug in numbers and come up. I'm going to always ask you ratios if you get a question like this, as you had on the homework. So suppose we say, let me see how it was in the homework. Suppose the surface temperature of the sun were 12,000 instead of 6,000. Then I say temperature, of this new sun equals 12,000, which equals twice the temperature of the real sun. So I put a prime to show that that's the change, the new one. How does the energy, well, let me use 2 and 1, we can do it either way. Then the energy in this new case with this new sun compared to the original energy from the sun is equal to sigma T2 to the 4th over sigma T1 to the 4th. And we've seen this enough times now that you know that the sigmas cancel out. So it's T2 up to the 4th over T1, and we can also write that as T2 over T1 quantity to the 4th. Maybe I'm going to erase this to make sure you can see what we're doing here. But this is 2, isn't it? T2 over T1 is 2. So it's 2 to the 4th power, 2 times 2 times 2 times 2, which equals... We could go the other way. Suppose we have a star that has a temperature of 10,000, and what would it be if it was 5,000? That's half as much. So it would end up being to the 4th power would be half, and 1/16. The other thing, this tells me the ratio, how much more energy it gives off per second. The other thing we could say, if the sun at its temperature of 6,000 degrees looks yellow, right? And we have an equation that says the wavelength of maximum energy intensity equals some constant divided by the temperature. Inverse relationship, right? Temperature goes up, peak gets smaller. So it's an inverse relationship. So in this case, here's the intensity for the sun, which we said is yellow light. The intensity, the wavelength of maximum intensity in this new number 2 star is equal to the same constant. I can give you the number, but you don't need it to do the arithmetic. Divided by this new temperature. And so how does the new wavelength compare to the old? You can see we can go through the arithmetic. And it turns out that if we keep going through the arithmetic, lambda max 2, lambda max 1. The constants are going to divide out, so it'll be 1 over lambda, or 1 over T1, or T2, divided by 1 over T1. Right, because the constants will cancel out again. And it's a little tricky when you have things like, a denominator in the denominator. And so if you multiply the numerator and denominator by the same number, you don't change the value. So if I multiply the numerator and the denominator by T1, I get T2 over T1 because these cancel out. But it's kind of intuitive. It's going to be half the wavelength, right? I mean, you know that twice the temperature, it's going to peak at half the wavelength. Pardon? Yes, thank you. We should edit that so the people watching it at home don't see I made a mistake. This is what this chapter was about, right? There's one more question here. Oh, and then there's one that deals with telescopes. What are the 2 key properties of a telescope? What are they? What are the 2 key properties of a telescope? You don't need to see this. Okay, what's one?
Light collecting area.
Light collecting area. We want to build it bigger and bigger so it can collect more light from those distant objects, so that that amount of light that strikes it gets focused to something we can look through with our eye or we can look at with the camera. So the bigger the mirror, or the bigger the lens, the more light it'll capture, the brighter the stars will be, and it can gather enough light that ones that are below the threshold to see will be able to see. And that depends, on how big it is, which is the area. So if something is twice as big, it has 4 times the area, because it goes as radius or diameter squared. We okay on that? So we have a telescope that's 16 inches, 0.4 meters. At Kitt Peak in Arizona, there's a telescope that's 4 meters in diameter. So how much bigger in diameter? It's 4, we're 0.4, it's how many times bigger? 10 times bigger. So its area is 10 squared, or 100 times. It has 100 times the total area of our, that's awfully big, isn't it? So it can, in a sense, see things that are 100 times fainter. That's why we want bigger telescopes to gather more light. The other thing that the text mentions is what? Angular resolution. So what do we mean by that? Alexa?
Yeah.
What do we
See more detail.
Okay, we can see more detail. Things that are too close together to see as separate with a small telescope, a bigger one will resolve them. That's a word, that's a common word. It'll resolve them into 2 separate stars, for example. Or we'll see more detail on another planet. That's an important factor if we want to make out and learn about the objects we're looking at. We don't want to just know how bright are they if there's an opportunity to learn more detail. Especially when we look at nebulae, we can see filaments. We can look at clusters of stars. We can see the individual stars in those clusters. They're not all blurred together. Now the bad news, and we'll go over this in lab next week, is that the bigger the diameter, the better resolution you get in principle. But the problem is we all sit under this blanket of a turbulent atmosphere. Winds blow through, there are cells in the atmosphere of gas that are ascending and descending. They blur the image. So there's only we can only get it so small on the surface of the Earth. That's why Hubble's in space. Is it in space to get close to the stars? 200 miles up doesn't get you very far, does it? But it's above the atmosphere, so it gets sharp images. Yes?
So, like last night viewing Neptune,
Yeah.
was it blurry because of the Earth's atmosphere, or just because of space in general?
There'll be two reasons. It could be blurry because of the Earth's atmosphere. And a star is, although a star is huge, it's so far away it's a point of light. The planets are not points of light. You can see their size. Those of you that saw Saturn, that was real clear. You could see how big it was in the sky. Neptune, you can do it, although it's smaller. Mars, you can see. Venus. So, part of the reason it's as big as it is because it's really a small disk of light. In terms of telescopes, I regret that I went through it as quickly as I did. I will come back when we talk about stars to talk a little bit about telescopes at X-ray wavelengths or infrared, because we'll be making use of those to study the stars. So what we didn't cover here, we'll pick up that. Important chapter, isn't it? This is sort of the tools we're going to use when we go to study stars in particular, to figure out their properties. We need to understand how to use these tools about spectra of light, where the energy peaks. We also need the tools about gravity, and that was the previous chapter, because we're going to see stars orbiting each other under their gravity. It's going to allow us to weigh the stars using Kepler's third law. Remember, Kepler's third law says mass of one plus mass of the other times the period squared equals the semi-major axis cubed. We will see stars in space orbiting around each other in elliptical orbits. And you see, if we can get the period squared, and we can figure out how far apart they are from each other, we're going to get the mass of the two stars. We're going to be able to figure out how massive are those stars way out there in space by using these laws of gravity. When we talk about solar system, then it's sort of practical application of getting a satellite that flies to Mars, or flies way out to Pluto, or flies by a comet, and then drops something on it. Getting these stuff. Okay, questions that you have about properties of light? Yes. Oh yeah, we were going to take a